So, question, please, and we have some time even for comments, and please.
Can you explain how this is false? Can you explain if you force the flow? If you force the flow, can you explain how you do the forcing?
Yeah. Forcing in simulations?
Yeah.
Okay, we have homogeneous and isotropic forcing.
On what scale?
White in noise. In what scales? In the scales, okay, forcing scale 1/3 of the horizontal scale.
Right.
Okay? 1/3. So we have separation of scales. Of course, not large.
So what's the magnetic Reynolds number on the scale of forcing?
Okay, magnetic Reynolds number here in the system is determined by, this is the definition.
It's 5, you say?
This definition of
What's L naught?
Reynolds number. So L naught divided by 2 pi, this is inverse K. F. Okay? Yeah, so this is a scale of forcing. Okay? So this is a value. So it's not large
No.
from one hand, but in many mean field effects, we know that main contribution comes from the maximum scale of turbulent motions. I know only one exception from this situation when you have magnetic fluctuations caused by tangling. Okay? In this situation, main contribution comes not from maximum scale turbulent motions, it comes from the small scales. This is the reason why B squared divided by mean value B depends on magnetic Reynolds number. But in principle, we study a lot different kind of mean field effects in different fluid dynamics regions and MHD. And we found only one example when there is a contribution to the mean field effects from the small scales. So we don't need to have developed inertial range in order to have dynamo. There is some constraint. Of course, we cannot have a scaling of the correlation time like a diffusive scaling, k to the -2. But it's very difficult to organize simulations in order to have such scaling for the correlation time.
So the question is then, you said that the mean field effects are coming from here. Do they get swamped by the small scale effects that are coming from high magnetic Reynolds number? The fact that you're at high magnetic Reynolds number.
Okay. Okay, of course it's possible to perform simulations with the high magnetic Reynolds number. And of course the effect should be. But you noted that resolution for such simulations is as follows. So first of all we have to, we need to have a box in that direction, in the direction where magnetic field, there is evolution of the large scale magnetic field. We have, this is log box in order to have moved with the maximum growth rate. And so this resolution is...
Yeah, I understand it's an incredibly difficult thing to do this, again at high magnetic Reynolds numbers. But you've shown that there is a mean field effect. Okay, fair enough. But the reason that David and I don't see a mean field is because that effect is really swamped by the small scale field. And you can't address that. So you can't say to David, the reason you haven't got your whatever it is because it's small shear is because it's a high magnetic Reynolds number. And the small scale effect is swamping large scale effects, which may happen for you, but I admit it's
But I'm sure if you have large magnetic Reynolds number and large Reynolds number, this effect should be. Because, you know.
Well, the effect might be there, but you might never see it. The effect might be there. All you see is the small scale field that's coming from the fact that you're at high magnetic Reynolds.
Yeah, I understand. Okay, but when I discuss with David these simulations, as far as I understand, so it's very important to perform simulations, first of all, without small-scale dynamo. So there is a range of parameters of Rayleigh number where there are no small-scale dynamo. On the other hand, of course, there is a threshold and shear. You cannot have very small shear because there is a threshold for generation. There is a threshold for generation of magnetic field in terms of the dimensionless dynamo number, okay, and or in terms of the shear. So maybe in your simulation shear was small. So you're under the threshold for excitation of large-scale magnetic field, because shear in your simulations is 1 divided by 50, 10 to the minus 2. Is it okay? In comparison, I mean, what does it mean, this number? So you take large-scale shear and multiply it by the L forcing divided by U less. And this L forcing means that you have 2 pi divided by Kf. So this parameter from one hand should be more than some critical value. Okay? On the other hand, you cannot produce light shear, otherwise you have shear-induced turbulence, and so, at least in our simulations, here we don't have separation of scales, because if you have shear at the larger scales, and the production of turbulence by this shear is of the order of production caused by the forcing, so there are no separation of scales here in this situation. So we have some two limitations, but nevertheless in these simulations we avoid generation of turbulence caused by the shear-induced turbulence. So we have a parametric space where these conditions satisfy. Okay, this is the first. The second, there is a threshold for excitation of large-scale magnetic field in a shear number. So maybe if you, in your simulations, increase shear number, maybe there is a...
It's not clear that
So,
it's not clear. It's clear.
right, honorable gentlemen, it is. Let us slightly organize discussion. Your short question and then your short question.
So the evidence for the phenomenon, I mean the evidence for the shear current effect in your simulations comes from the fact that you actually do see a large-scale magnetic field in the simulation.
Yeah.
But on the other hand, it contradicts the theory because the growth rate is not proportional to the shear squared.
Okay.
It's proportional to the shear.
But if
So if you alternatively ask, what is the evidence for this effect being due to the incoherent alpha effect, then you could also say, okay, the evidence is yes, because it does produce a large-scale field, the simulation, and in the incoherent alpha effect, you would expect the growth rate to be proportional to the shear, not the shear squared.
Yes.
So in that case, you have 2 points against 1 point in the other case.
Okay. The answer? Okay. The fact that we don't have scaling S squared just implies that maybe we don't have the mode with the maximum growth rate inside the box. This is the first point. The second, just a moment. The second point, it's not clear numerical simulation in the sense we also have generation of large-scale vorticity. Maybe there is a fact of generation of large-scale vorticity to this. Okay, so in order to, we'll study this effect. We will study numerically in the framework of mean field theory, generation of large-scale magnetic field in the case of shear current effect in the presence of generation of vorticity.
David, please your question, if possible, short, in a short form.
To answer Axel. Okay, could I? Okay, the second about the incoherent alpha effect. If we understand that incoherent alpha effect, in the sense which we described, which in the setup which was in the setup which was formulated by Krachman, then we have two separated sources. So definitely in these simulations there are no any included alpha effect, because what is the source of fluctuations of alpha? You need to have source of fluctuations of alpha which separated the scales.
It's comes
with
from the
the
finiteness of cells in the horizontal plane. That's exactly the reason. So you have a forcing wave number of 3. That means if you average over 3 cells times another 3 cells, that is 9 cells, then the effect of fluctuations will be 1 over the square root of 9.
in these simulations we average over x and y plane,
Yes.
and there is only variations
Yes.
in z direction.
Yes. And so
In
you
z direction there is a large separation of scales.
yes, but you have
And-
fluctuations at any given plane.
Dear colleagues, we have somehow separate between questions and scientific discussion. We have additional scientific... David, please, your question or comment. Answer, please.
Maybe we
It would be even more welcome.
That number there, I mean, in the calculations we were doing, you got URMS on the bottom, but we were interested in the case where shear is big compared to alpha, say. Alpha, as we know in ours, is nothing like URMS.
Yeah, I understand. Yeah,
So that number is so the shear in some sense is not small.
yeah. Of course, yeah. Okay, I understand this. The simulations are very good, but yeah. Okay, but
Simulations, I'm just
okay.
after telling you that is not necessarily the correct number to look at, depending on what question you wanted to answer. We were answering, can shear overcome a lousy alpha squared dynamo? And a number based on alpha, which is a velocity in that formula, means the shear is big. And the answer is still no.
Okay. Okay. Yeah. But as to the incoherent alpha effect, we show that using it's possible to write just 4 lines and show that using the second order correlation coefficient, which is considered many of people as exact theory in the frame when this theory is applicable, then it is easy to show that there is no generation of large-scale magnetic field due to homogeneous kinetic helicity fluctuations.
Well, I beg to differ because I'm looking at you. I was looking at your paper just a few minutes ago, and the coefficient which you claim is positive has no definite signs. We can discuss this later.
So, yes, great idea. I strongly support it to discuss it later in the framework of discussion, not in the framework of no. Just now we have questions.
Okay.
And the time is spent, and now I have to. I have the last duty to invite the moderators of the following discussion, Rainer Beck and Bhutan Vishniak, and I hope that you can give all opportunities to say everything what people desire to say. Thank you very much.
Yeah, you want to use it or what?
Well, I should say something about the division of labor here. You see, Reiner's going to cover the observational discussion, and I'm going to cover the theoretical discussion. And similarly, I was present for some of the talks today, and Reiner was present for some of the talks. There's not a perfect overlap here.
I was present for all talks.
Oh, okay. Well, I was not. Let's be honest.
Doesn't mean that I understood them.
So, it's been a contentious day, particularly on the theoretical side. And I think that we could easily take up the entire discussion period just with theoretical issues. But I thought we would try to be as calm as possible about it. for myself, let's say, starting out listening to this discussion, I am struck by the fact that it's amazingly hard to produce a good kinematic dynamo, and when one seems to be produced, it's very hard to decide why it's being produced. I used to have a simple answer when confronted with these kinds of things, which is that I would say, well, you know, it's all the magnetic helicity current, you're not doing the boundary conditions right, and so on. But of course, that really doesn't apply when the fields are small to begin with and we're looking at the initial stage of growth. And the theory there should be straightforward, and evidently it's not. And although it seems futile to accept perfect agreement, I would like to hear some more thoughts from people to start the discussion out on why it's so hard to apply what seems like a perfectly straightforward kinematic dynamo theory to simple computer simulations.
You mean large scale?
Large scale. Because small scale, we can all agree that generically disordered magnetic fields are easy to produce from turbulence. So I don't see that there's much controversy there. Young man.
Well, there's two reasons, right? I mean, one reason is this thing is, even without a small scale dynamo, it's massively fluctuating. And so when people do new field theories, they're using to write angle brackets around something. And there's a kind of assumption that U cross B average in magnitude is something like the average of U times the average of B. And indeed, the lower n or short flows with small correlation. That's right. The picture of Parker loops all adding together to give one nice big thing pointing in the right direction is probably right. And at high Rn, there is plenty of U cross B. And it's all over the place. If you want to think of Parker loops, one of them is twisted, 483 times, and the guy next to him is twisted 482 times. And averaged over the box, you get almost nothing. So even if you can manufacture it so that you're in a high RM but not so high that you don't have a small scale dynamo, what an angle bracket means, these things are almost like random events. And you need a heck of a lot of averaging to even pin down the answer. So that's why I think there's a problem. There's a problem even in defining and calculating mean induction as high RM, but not even high but not so high that you've got a small scale dynamo. You can manufacture that sometimes. So that's one problem. And the other problem is if you boost RM high enough, what you get is a big, healthy, small scale dynamo. And that is what you see. Now you might be able to average that in some clever sense over I don't know, some kind of ensemble average, possibly. Not sure quite how. And out of that ensemble averages emerges a different piece, which is the large-scale piece that we've all been looking for. And you never see it. That's not what you see. And so it's a useless piece.
Yeah, I'd just like to back that up by saying you can think of the alpha effect as being an order of magnitude more sensitive than, say, turbulent diffusion. You can do a thought experiment, you can do a numerical experiment where you take cells and you decorrelate them in space. So what this one's doing doesn't seem to be, correlated with the nearby cells. And then you can have a look at the turbulent diffusion of a scale, I say, and the EMF. And you can choose your decorrelations. So Alice Courvoisier, our postdoc, has done this. You can choose your decorrelations from a random distribution. And you have a look, and the turbulent diffusion is not sensitive to how you decorrelate the flow. On the other hand, the alpha effect, as soon as this cell doesn't know what the next cell is doing, it's staying set, which it won't do at high Reynolds number, high RM, you get a lot of EMF, you get a lot of induction. And when you average it, your spatial decorrelations wipe almost everything out, and alpha goes small. And that's an inescapable fact that in turbulent flows at high RM.
Inescapable except for what stars actually do.
Right. But they might not do it by, mean field theory.
I've got two explanations, but another. I would like to give some small sketch, if possible. Suppose we try to reproduce all increments in all scales. What do we observe? We observe this one, this is large scale window, and this is small scale window. In order to reproduce it, we need scale separation. If not, just will be the same. So, for definition, in order to reproduce large-scale dynamo, we need scale separation. What actually happened if we so lucky and we can to do it? Well, we can do it. The magnetic field will be, of course, another. In this, we produce large-scale magnetic field, small scale, and after that, some transient as a result of tangling of large-scale magnetic field by turbulence. So difference between large-scale dynamo and small-scale dynamo is very simple in this sense. If small-scale dynamo exists, this is for large-scale, and this is very dynamic. And this is for small-scale. It's magnetic one, and this is magnetic one again. So we observe in our simulation with Tarek and Alex precisely this behavior. My feeling that, by the way, if S is very small, you need more strong scale separation. According to our experience with Alex, we need, if you really have got 1 divided by 50, we need something much huge box simple in one direction. Huge, maybe 5 times larger than we had. So it's a reason. So first problem, and it's first problem. Second problem, that in the more clean situation with shear dynamo, unfortunately we produced dynamo of vortex dynamo, which redistribute and reorganize all large-scale motion. So when we produce, when we find S-square dependence, maybe just a result of this reorganization of motion.
Just to talk about the second point, I mean, the reason you found that is because you decided to do a kinematic dynamo by forcing a flow. Why do you need to do that? It's a kinematic dynamo. You just prescribe the velocity, and you can pick the velocity to be whatever you like. You don't need any large-scale rearrangement.
You know, it is, what can I say? In some sense, kinematic dynamo exists just in mind of theoreticians. Okay, if you use full system of equation, I mean induction equation and equation of motion, you definitely in small scale you've got dynamic situation practically immediately, and you should reduce turbulent dynamo somehow. If not, for example, in small scale you've got dynamic situation and large scale kinematic. How you can distinguish this situation?
You were saying, you're trying to do a kinematic problem, right? You're looking at growth rate.
Kinematic for magnetic.
For magnetic field. For magnetic field just, no.
Right? And you're saying that the reason things are not working is because your flow is not looking quite like you'd like it to do because of forcing and you've got this generation
Of generation, yeah.
So all I'm saying is you're doing a kinematic problem for the magnetic field. Choose your velocity field to get rid of this problem.
You know, unfortunately, the situation is very bad in this sense. The coefficient, sigma, in our calculation, for magnetic field, 1 divided by 30 approximately. And for ADIS, it's 1 divided by 2. It's amazing, but matter of fact. So we believe it's true. So simple difference between growth rate, approximately 1 order for the same scales. It's a problem.
Perhaps we can hear from someone at Axel.
The simulations that David showed, they were non-linear, and so one should not compare those against or use those in connection with your question. What do we know about the kinematic regime? So it's quite possible that in the nonlinear regime, the smallness of the alpha, of the averaged alpha, is simply explained by the catastrophic quenching, which we know how strong it is supposed to be. And of course, for very large Reynolds numbers, it is very strong, and it must be catastrophic, because there's no flux, there's also no current, because the average field is a uniform field. The curl of a uniform field is zero. In the kinematic regime, it was brought up that the Courvoisier results, but they are for the time-dependent Galloway-Proctor flow, which we know has very special behavior as far as the alpha is concerned. If Karl-Heinz Redler was here, he would have talked about the SOCA results and SOCA results beyond SOCA for the time-dependent Galloway-Proctor flow. So that there is indeed a highly unexpected behavior when observed for such flows. So I should emphasize the result that Sharon Yasur will talk about tomorrow, that you have, most of you have perhaps seen in the literature already, where where the kinematic alpha effect for isotropic, isotropic fully helical forcing results in an alpha that grows for small magnetic Reynolds numbers linearly with the magnetic Reynolds number and saturates at 1/3 of the RMS velocity. So that, I think, should be really used as a benchmark here for kinematic results, and that has been tested for up to an RM of 200. What? 220. So I think that's what we really know for sure now, and these are very clean calculations of the alpha. Regarding the eta, these results with the test method are also very clean, of course, and we know the off-diagonal components, and we know that the sign of the off-diagonal component is such that that the shear current effect has a wrong sign. The effect grows for small RMs with a wrong sign, and then for larger RMs becomes smaller again and still has a wrong sign and does not show any tendency to change its sign.
What RM you?
As you know from the paper, I mean, we go up to typically 200.
Strange.
Andrew?
I just wanted to say that to me, actually, the small-scale dynamo is the main culprit. If you do not have the small-scale dynamo, even in U cross B, the small b is not that large. So it's still possible to get the alpha to be roughly okay. It looks like. Once you have the small-scale dynamo, of course, there is a certain limit up to which the alpha seems to work in the simulation which Axel is talking about. But after that, suppose you want to ask, can I grow a field from 10 to the minus 19 torts to a microtors? And the small scale dynamo grows on a time scale of 10 to the 7 years, usually on 10 to the 8 years. Then I will be worried, of course. And it's not yet demonstrated, I think, and it should. It's something which is a worrying thing that in the presence of the large fluctuations of the small scale dynamo, whether the fluctuations in EMF overwhelm the mean.
Sorry, your definition of small scale dynamo, this is dynamo with zero mean magnetic field.
Yes.
Is it? Right? Okay.
So from that point of view, I think this work about fluctuating alpha is interesting, but I think the EMF itself is fluctuating, and one has to find out how to deal with these fluctuations. And I mean, I think it's a real problem, and we have to fix this slowly and steadily.
David?
Well, Axel said that
No problem at all.
fluctuation of alpha. It isn't, but even if it were, what Canada was just saying is exactly right. It isn't there for whatever reason, and it's not to do with saturation of alpha, because we've looked at very weak fields and the things we've looked at varying RNs. It's not saturated some sense, because what you see, as Andrew said, is this small-scale dynamo. You can argue to your heart's content about this, that, and the other. The bottom line is that you have a calculation with very helical turbulence at quite high RM, and you see no mean magnetic field. You see no large-scale magnetic field. And you can try and explain it away in all kinds of things. But that's the fact.
Why no? No, we've got.
I speak about his.
You need additional scale separation or increase your shear.
But in your simulation, you talk about vorticity redistribution, so you have velocity on a large scale, or not?
We have the velocity in the large scale. First of all, we have enclosed shear.
Yeah.
Yeah, shear. This is large scale velocity. And due to the presence of shear in small scale turbulence, there is a generation of also large scale vorticity. So there is additional large scale field. Yeah? But it is a big field.
Well, are you driving your large scale velocity?
Okay. In this simulation also there is excitation. Of course, we try to avoid calculations where there is really a generation of large-scale vorticity. But here we have generation of large-scale vorticity, but the level of newly produced shear, large-scale shear, is that the production of turbulence due to the shear is much smaller than the production of turbulence due to the small-scale velocity. Understand?
Well, no, I'm trying to get out what the velocity spectrum is. Are you driving?
Yeah, velocity spectrum. Okay, what is the velocity spectrum? Okay, forcing is white in noise, since equation is not so dependent on smaller scales, I mean generation of large scale magnetic field. So the main contribution to the generation of large scale is from the maximum is the forcing scale. Okay? But production of turbulence, additional turbulence due to generated vorticity is very small in comparison with the production caused by the small scale velocity. So we can forget about these additional anisotropic fluctuations caused by the shear because their effect on the turbulence is small. Okay? And, for example, when we include rotation, when we include in the simulation uniform rotation, we don't observe generation of any generation of large-scale vorticity, but we observe clearly generation of large-scale magnetic field. We haven't yet checked what are the scalings of growth rate of magnetic field versus shear. And so this is simulations in the progress.
But this thing falls into what you call shear current, or not?
Okay, let us separate theory from numerical experiment in the sense that when we perform experiments in numerical simulation, this is real experiment. We have to forget about theory and just have clear experimental results, and then we try to.
No, I'm just trying to understand the physics of your behind your numerical results. That's all.
Yeah, we believe that the main reason for generation of large-scale magnetic field is the shear current effect. Okay, so the effect caused by the additional term of the electromotive force, which is a vector product of background vorticity by the mean electric current. This is the main reason for generation of large-scale magnetic field from theoretical point of view. Okay? Since we don't have a clear experiment now, okay, we cannot say that the theory of shear current doesn't exist because we have such simulations. No. What we have, what information we have, that if we impose on the system large-scale velocity shear in the turbulence, large-scale velocity shear,
we do have generation of large-scale magnetic field. Now, we don't know exactly, we don't know if it is main reason the shear current effect. We have to prove this. But now, since in the experiment, which is very similar to the theoretical setup, is similar, but we have obtained scalings which are not follows from the consideration of, don't follows from the fact that the maximum growth rate we have. But if we don't have mode with the maximum growth rate, scaling should be the same as the simulation shows us.
But there's all kinds of dynamos which are at low end, they like to be long, you know, in one direction. If you're more or less, if you were really dependent on X and Y at lower end, then there's a whole slew of dynamos that like to be long in Z, and they're not.
Okay, but when we include rotation, we perform simulation with unit force. And we found that there is dynamo.
Oh, okay, excuse me.
Yeah.
This is becoming a dialogue, which is okay, but probably not online.
Yeah, okay.
Do we have any questions or comments or passionate arguments from other people in the room? Okay.
I have a comment for Igor and a question for Dave. So have you tried to determine the critical Reynolds number at which the large-scale dynamo really stops working? You said that you have varied the Reynolds number. So can you determine such a thing?
Of course.
Does it at which Reynolds numbers it does work then? Because I don't remember, perhaps I'm just forgetting things, but I don't remember seeing any example of a working large-scale dynamo from your
We
talk.
don't have a working large-scale dynamo, but if you
Not
were
even with a
if you were
low Reynolds number.
if you were close to onset, so if you were close to onset of convection, for example, then you would get. I mean, that's what Sauer showed a long time ago. But then you're in kind of the ordered convection regime.
And Igor, one question. How do you know when you then push in the uniform rotation? How do you know that then you don't get MRI? How do you get rid of MRI?
Okay. Okay. So you said the following, that maybe the reason of generation of large-scale magnetic field in the presence of uniform rotation is an MRI instability. Right?
Yes, it can be.
Okay.
No, but the
I'm
time
working
scales are
on
different.
this. I don't want just now to discuss this
So the
problem
growth
because
rate is
this is in
proportional
progress.
to
It's
X.
possible to separate these two problems, MRI and generation of large-scale magnetic. This is possible to do, but maybe we will leave this question for the future, okay? Maybe in 2
Maybe-
months we will answer
Maybe one
this.
last comment, and I should let Reiner have a shot at this. Axel?
I believe there is agreement that theoretically we expect that the onset of large-scale dynamo action depends not on Rm primarily, at least not if Rm is larger than 1. It does depend entirely on the amount of shear and the amount of scale separation that we have. These are completely geometrical aspects and independent of Rm. By contrast, the small-scale dynamo action entirely depends on the value of Rm and the value of Pm, the magnetic Prandtl number. In particular, we know of situations that in the case of small magnetic Prandtl numbers, 0.1, for example, or 0.05, the critical value of Rm for small-scale dynamo action is on the order of at least 400. And actually, it's so large that we have no successful dynamo simulation yet, a direct simulation at a Prandtl number of 0.05, and we have reached a magnetic Reynolds number on the order of several hundred, and there's no small-scale dynamo. But clearly, in such a regime, large-scale dynamo action must exist. So I think it's wrong to not go for these small Prandtl number cases. and to exclude small-scale dynamo action that way.
Right.
And then, of course, and then you are probably finding that you don't find a large-scale dynamo action, and the reason is simply that you have not exceeded the critical value of the dynamo number, which does not depend on Rm, but does depend on scale separation and the amount of shear.
And influence of catastrophic quenching too. That's another story. Influence of catastrophic quenching.
In the what? Say again.
Influence of catastrophic quenching.
Of sheer current effect.
Of shear current effect.
Not
Never mind, it ain't dynamo.
Yeah.
It's the same problem if you get magnetic release.
Because you
That's what, yeah,
okay,
right.
Some discussion you said that why we speak about catastrophic equation, there are no alpha. But catastrophic equation quenching exists also without alpha.
Yeah, that's right. Correct.
Yeah?
It still doesn't. It doesn't matter what's being. It doesn't matter what's being quenched. You're not going. It's not there. I mean, this is a very philosophical thing.
It used to be the Greek alphabet which is being quenched.
That is there. There's all kinds of things that aren't there. We could discuss at length why they're not there and how small they are. But there's something really big that's there.
I think this can go on forever, and it will go on over dinner, but in the meantime, let me step down and we'll go on to the next phase.
Yeah, I'm sorry that I'm not able to contribute to that discussion, so just give my personal view of what's going on here. So I must realize with some surprise that there's still some basic discussion about whether the dynamo can work or not. And I think that has not really changed in the last 20 years as long as I'm in the business. So what does it tell us? It tells us that theory and models is really difficult. We should have plugged it in. Yes. Sorry. And so as an observer, I'm a pragmatic person. So what will finally be the success of the dynamo models? It will be that we can really show that it works. And I think so. The nature shows that the dynamo really works. And so the solar people, the stellar people, and also the galaxy people have shown that dynamo are really operating in the universe. So the rest is then up to you to explain how it works. But we as observers, we would really like to understand a few basic things, much more basic than what you are discussing here. And I've summarized a few questions from observers, if you want. There may be many more, and I would like to get comments on that. So if we write proposals for our observations, that's always the same question, and also in committees, always the same question. What are the timescales of dynamo action? So is it really clarified that within a lifetime of a star, okay, fine, but lifetime of a galaxy, the dynamo can really generate the field as it is observed today? And so there's still some controversy in the different models. So this is a number we really have to get, and we have to argue with that. So people are arguing with several 10 to the 9 years from old conventional dynamo models, and this is obviously not true anymore. But if I listen to the discussion today, if there's so many uncertainties, how certain can we be about these numbers? So that we need that. And then, as Andrew has nicely shown today, the superposition of dynamo modes is the normal situation in galaxies, probably also in stars and sun. I don't know how many dynamo modes you need, and I don't see any good model which predicts how many modes they have, and especially why the modes have even similar amplitudes, as Andrew has shown today. So this is really a mystery. I remember that the basic modes, the ground modes, should be exciting. The higher amplitudes, and maybe you get some other ones. Field strength. So are there chances for super equipotential? So should we as observers look into that further on? Or do I believe people like Anwar would tell me, oh, this is all problem of observation, so you should really check your data carefully and think about your assumptions, and if you do all that carefully, then finally super equipotential will go away. And last point is that also Andrew has shown today the pitch angle problem. So pitch angle depends on the dynamo numbers, a combination of whatever, maybe the Potsdam combination or the Newcastle combination of dynamo numbers. Anyway, it roughly agrees with observations, but there are clear discrepancies. So there must be something which forces the dynamo to take care of what else is going on in the galaxy, like a density wave. So these are things we really have to know. This is much more fundamental and basic as what you're discussing here. And really urge you to help us with these problems. Because if these are not solved, then we get trouble with our colleagues who don't believe in dynamos in any way, and that even don't believe in the importance of magnetic fields. And they tell us that it's unimportant if the pitch angle deviates so strongly from what dynamo predicts, and this clearly shows the dynamo doesn't operate. And then you have to look for alternative models, which just explains everything with shear and with gas flows, and the magnetic field is totally passive and will be just transported around. So why should we bother about dynamos at all? So these are the few introduction comments, and then I just repeat my last transparency from my talk. So first we would like to get really good kinematical dynamo models. And in the last 10 or 15 years, there's a lot of basic research in dynamo theory, but we really need models for galaxies, and probably the same also for stars, which are realistic, which include spiral arms, bars, and outflows, which has become now really important because the helical outflows are really important. This has to be done again because the old models, they do not work. And the next step would be dynamical dynamo models, including the back reaction. Are we dreaming? So what are we discussing about? So can we expect that? What's it in next year, 5 years, 10 years, never? So when will there be really dynamical dynamo models? And then, again, we need a new atlas of dynamo modes. So we don't produce specific dynamo, not only dynamo models for specific galaxies, but we just trace through the possible parameters of rotation curves, of star formation rates, and then let's just see what dynamo predicts, and then make an atlas like Detlef Elster and myself have done in '92. But not only radio maps, but also including Faraday rotation and Faraday depolarization, like something we can compare then with observations, and then that will show us whether a dynamo is able to predict what we can observe in future. And finally, just to remind you that evolution aspects in galaxies are quite important. So present day structure of magnetic field is just the product, the result of a long evolution of a galaxy. If the dynamo really takes 10 to the 9 years, a lot has happened during the lifetime of a galaxy. The galaxy was much more active in the past, has suffered a lot of inflow of gas, of mergers. All that has to be included, and the question is whether that can be done in very near future. So these are my request to theory, and the final introduction remark is I know that there are also requests to observers, and I've made a very short list because I expect more requests to us from you, because this is a group of theoreticians and observers. So clearly we have to provide a spectrum of dynamo modes. This is something we have to do, and we all know that we have to measure helical fields, so this can be done observationally. So we have ideas how to do that, and we will try to do it. Whether it will be possible within the next years, it's not clear. And we have to measure field evolution, at least in galaxies. We can go to distant galaxies, we can do it, and this is one of the key projects, for instance, for the SKA, and I'm sure there will be many more of these points to do. So I would like to take the next, 15 or 20 minutes to discuss how theoreticians and observers can come back together and work on models and observations. So this was my brief introduction, and I'm sure there will be comments or ideas or more points. Can do, please.
Yeah, I just wanted to remind one thing about which Anwar first taught me, that the pitch angle means that the dynamo is necessary. See, the fact that it's not completely tightly wound up means that it's not frozen into the flow, which means that it has to slip, and that means there has to be turbulent diffusion, and so there has to be a generation to compensate that. So although we may be arguing about how the theory works, I mean, it has to work, of course. Now, the other thing about high redshift, which is what one would be interested in, is that even if the mean field dynamo doesn't work, everybody agrees that the fluctuation dynamo works. But of course, there's also a controversy about what's the scale in which the power there is. Okay. And you can always have, during structure formation, turbulence being driven by supernovae, by structures collapsing into forming galaxies and all that. And you'll always have growth of magnetic energy. And I think you'll always get rotation measures through this, just like we have found for the cluster case. So from the observational point of view, what you need actually is the correlation, just like you have the rotation measure map. You need to get something at higher redshift.
But it would be good to have some idea of how long does it take, what Z do we expect the first galaxies to be bright in radio synchrotron, and how long would it take until the first ordered
No, you
fields
always
can
have
be
radio
observed?
sources, high redshift. You see, the thing is to test mean field dynamo. If the growth rate is 10 to the 8, 10 to the 9 years, you don't need to go back far in redshift. You just need to go to redshift of half. And you have enough look back time to find out whether the field is much weaker or not much weaker.
It doesn't appear to be much weaker.
And it doesn't appear to be much weaker, right?
So you would say this is our task to find out whether it's 10 to the 8 or 10 to the 9 years, right? Or, okay. So.
My question is, in what sense you've got contradiction in question of pitch angle? Value or radial distribution, say? What's the problem?
I think mainly the value, the overall value. So it seems that all galaxies more or less have a decreasing pitch angle, and according to Anwar, this is what theory, what models predict. So this is not the problem. It's the overall level of pitch angle, which is offset.
And what how to say, ratio of theoretical prediction and your observation?
In case of M33, there was a factor of at least 2 difference between them, right? Or it was 40 against 20, or
that was just a total back of the envelope calculation. It wasn't comparing any serious model. It was just plugging up parameters that weren't known. I plugged out of the air 2 days ago. I mean, if you want to consider it a bit more carefully and dig around to find some more information, you might be able to easily make that.
Pi over 2 is close to 2. Root of 3 is equally close to 2. Just add root of 3 to this estimate, you will get it right, if you wish.
I don't think it's such a big problem.
It's an order of magnitude estimate.
I do not agree. I think it is a problem because it's systematic in many galaxies. Okay, Axel?
I mean, the talk that we heard later today showed clearly that the pitch angle has to do with the ratio of alpha to the shear. And if you look at the models, which model are we actually talking about? Was it a model with alpha quenching or without? Because of course, if we put in an alpha quenching, that makes this alpha all of a sudden much smaller compared to the shear, which is wrong. The real quenching does not work like this. The real quenching works like with the ejection of helicity. And so that may perhaps be the solution to that problem. If the models were simply ignorant regarding the
so we need practically a new formula where we can observe.
Of course, yeah.
Of course. Let me say a small comment about shear current effect. This mechanism normally gives a super equipartition level of mean field very often.
So you would say that this is nothing we have to worry about. This is something which may tell us something important.
No, my opinion is a little bit another. In some places, say in central plane of galaxy, maybe this phenomenon important. And in the central plane, you really can produce more strong field, but maybe with wrong pitch angle, and we should check it.
But what we would like to know is, would you expect the super equipartition more in the inner parts of galaxies, in more active parts, or more in the outer parts?
In the
inner. This is opposite to what we find.
Okay.
With this real nonlinearity, at least with the vertical fluxes, due to the just vertical advection and the essence flux, you can make this estimate. It's very close to the one which I mentioned today. It's just that the difference is more or less trivial, and you do get what is observed. In this sense,
within the
of
factor
course,
of
it should be further detailed, but at least the first attempts are quite successful. So these nonlinearities don't change the estimates too much. But regarding the time scales, when people refer to 10 to the 9th, for the dynamo, kinematic dynamo time scale. It's a huge exaggeration. It's a pre-Copernican view of the dynamos.
So what is the
the
number we should use in
the
proposal?
time scale
Is it
for
to the eighth
the classical dynamo near the sun. And the sun is not the center of the universe. Within our galaxy, just at the distance of half the solar distance, the growth time is significantly shorter.
So is
in
there
other
really-
galaxies like M51, the time scale is factor of 10 shorter. So when people refer to the value obtained for the solar neighborhood of the Milky Way as a general and universally applicable estimate for the dynamo time scale, it's a huge misconception.
But it's very robust, so it appears often and often in literature. So this is
No. Just because people keep this pre-Copernican view of the universe is the only reason. They take the solar value and extend it to the whole universe.
But then somebody has really to propagate that. So the same problem with the field strength. Everybody's using 5 microgauss, the typical fields in galaxies. And I'm telling since 20 years this is a solar neighborhood.
And what I'm saying now,
So
I'm telling for the same 20 years.
So the typical numbers
we doing the same
problem.
thing for 20 years. Still people boldly use these solar values.
I'm slightly successful now, so people start to change their numbers. Okay, and Thorsten.
I would like to add a few things to your wish list to the theoreticians. Not only galaxies are laboratories for dynamos, but also galaxy clusters, and there we don't have helical dynamos. We can make splendid simulation of galaxy clusters of structure formation. However, usually we are not able to resolve in these simulations to resolve the length scales on which dynamo action is taking place. But for many phenomena we are looking at, like radio emission or transport processes, we would like to have an idea of what the magnetic field should be in this environment given some dynamo theory.
Thorsten, sorry, I think we have a topic of clusters tomorrow, so maybe we would better shift that discussion to tomorrow's final discussion. Is that, I think this is the idea.
And will you present your wish list then again?
I don't know who's presenting the wish list tomorrow, but we can then combine it in the end. I think this...
Tomorrow's moderators are Mike Proctor.
I have really finished with my...
Okay, so it's no chance to expand the wish list, so okay, then we do it now.
No, but you want something from the observer or from
Okay,
the
just continue.
From the dynamo people, their recipes, given their dynamo theory, how the fluctuating field should evolve as a function of properties which one can measure macroscopically in a simulation. So that one can put something into simulation and add to a galaxy cluster, well, a proper magnetic field profile, and then calculate radio emission and observable quantities. And maybe distinguish between dynamo models if they differ in their predictions.
And this is, I agree with Thorsten. For example, here everybody agrees that the small-scale dynamos are sort of better understood physically, fundamentally, objects. So what are they, if they're understood, can somebody tell, just go there and tell what are the properties of magnetic field produced by small-scale dynamos then? Okay, let's agree that mean-field dynamos are poorly understood. But most people now say everything is, well, swarmed by small-scale, so what are the properties of that physical system? What are the typical scales, filling factors of magnetic fields? Are magnetic fields in filaments, ribbons? What are their filling factors? Is it locally helical or is it not?
So you're believing that the observed fields observed by you and other people, they are cannot fully be explained by mergers, by
well, mergers are the driver.
flows. So you think, is there any observational indication that you need more than that? So,
no.
From your talk yesterday, I had the impression that you can explain the observations with just with interactions and.
No. In the simulations, there were no self-consistent magnetic fields. We just put a recipe by hand, And I would like to improve this recipe. But in order to do so, I need somebody telling me, okay, if you have these conditions, you should assume those fields. Or if you have these conditions in the last past this and that years, then the field should be like that.
Okay, add it to the wish list. Okay, then any more comments on that or on another point? Okay.
About inner or outer region, what do you mean? In R direction or in Z direction?
Oh, this is an average in radial rings in the disk.
So it is R direction. In R direction, practically, it's not so important, I guess. Z is true, because the middle plane is more strong in this
In that direction, we don't have observational evidence.
I think, yeah. So,
very
so
hard to
maybe,
measure.
may I ask a question from Thorstein? Thorstein, have you got in your systems some regular shear flow?
Yes.
So maybe it's another possibility, simply.
Sure.
Clusters.
Observe large-scale react except for the case.
What does it mean? Who knows what is large scale? If sheer enough reach, enough complicated, your large scale magnetic field will be complicated enough. It's a question of interpretation.
For example, I guess a position where galaxy filaments connect to a galaxy cluster, you have a constant infall, and where the matter falling into the galaxy cluster dives into the cluster atmosphere, I would expect that you have more or less
shear-like flow.
Shear-like flow, at least in the time average.
Oh, interesting to estimate shear and other parameters and compare with the theory.
Or if you tell me, for example, translate shear in magnetic field like that, that's something like one can do.
From the principal point of view, it's possible.
When you say that you need a new atlas of dynamo modes, there are two things which I wanted to mention on that. First, this atlas will look simple, just one axisymmetric mode.
Yes, please.
That's nothing else. Because in thin disks, only one mode generates. What the other distortions from axisymmetry, from which Andrew was presented today, most probably, not necessarily, but most probably in most cases, can be explained by just distortion of this basic axisymmetric mode, by the spiral pattern or by total asymmetry or global asymmetry of the galaxy. But these are not dynamo modes. In addition, if you add depolarization to that, then you are talking, and plus Friday rotation, then you are talking about the atlas of something which occurs in a parametric space, in the space of parameters, which has something like 10 dimensions. How you make an atlas of 10-dimensional parameter space, it's unthinkable.
Yeah,
and this is the problem, because you cannot simply classify, because depolarization immediately introduces enormous complexity. What Brian was presented today about these canals. Look at the complexity of that phenomenon.
I think this will be a task for something like a joint group of people who just clarify what are the essential parameters. So for the ionized gas, I would say that no details are needed. We just use a smooth distribution of ionized gas. The same for the cosmic rays. So the problem is indeed the spiral arms. I think spiral galaxies have spiral arms. So if you say this is just a distortion, then I would not expect an amplitude of 1-to-1 or the 0 and 2 mode. So there is really a problem. So we have to include them. I think an atlas which just gives only one mode, this is not realistic, because we know already now that this is extremely rare. So galaxies have more modes. If you could say this is not a mode, this is a distortion.
A mode has a clear physical meaning.
Because the amplitudes are 1-to-1. It's not a distortion. It's not a distortion. They have almost
but
equal
they're not
amplitudes.
Dynamos are just one single
what
dynamo
else?
mode. The thinnest dynamo in simple kinematic model just excites one single mode.
Does everybody agree that?
No, I think it is true on the small Reynolds number, Reynolds number. But if your Reynolds number is high enough, many higher modes will excite it also.
But you're talking about large-scale dynamo, right? Where the Reynolds number doesn't
yes, amplitude maybe will be smaller, but they will be excited also.
No, the threshold, the dynamo threshold for.
If your Reynolds number is high enough,
It doesn't, dynamo doesn't matter. My Fellow's number doesn't matter.
Magnetic energy spectrum will be full from the large scale to the ohmic dissipation scale. All scale will contain the magnetic energy.
Okay. So can I ask some clarification as a non-galactic person? How important is the magnetic field in the dynamics of these galaxies?
This is, of course, a continuous discussion, and it seems that concerning the energy densities, magnetic fields are dynamically important on all terms concerning the sheer energy density, so not on the global rotation, of course, but anything else. So the energy densities are comparable to the radiation density, to the turbulent energy density, and all these seems to be more or less in equipartition, slightly super equipartition. So this is a system of different components, also with cosmic rays, which is relatively safe. At least on average there is energy balance between cosmic rays and magnetic fields.
So the magnetic field is dynamically active?
Yeah, it is magnetic.
And that means that considerations based on linear eigenmodes growing at different rates are simply not the way to go. You have nonlinear interactions between modes, which typically, once you have a well-established mode, tend to get rid of the other modes, and that's the situation that's normal. Of course, you have an inhomogeneous background here, especially with these spiral galaxies. So it's not at all surprising that the fields that you see reflect this inhomogeneity in their structure. I don't find it surprising that you get mode additions, because you have m equals 2 additions to some axisymmetric mean generation, then of course you get m equals 2 generated.
Enslaved-driven mode. It's not independently generated by the dynamo.
Well, I would say it's all part of the same mode. The dynamo mode, in a situation where you have an m equals 2 component of velocity, will always have m equals 2 bits of it.
Okay, thank you.
Yeah, but what happens is when long time back when Bjorn Wester and I looked at the non-axisymmetric thing, non-axisymmetric thing have anyway a smaller growth rate to begin with compared to the axisymmetric.
They might eventually be more.
Yeah, and so you have to really jack up the non-axisymmetry to make them comparable to begin with in the growth rate, in the linear kinematic problem. But of course, once they saturate, whether they will all mix, that will be...
I mean, studies in nonlinear dynamos and solar models show that it's very complicated which mode is actually realized.
So is there any chance to go forward on these non-linear models in future? Is just not possible with the present numerical possibilities?
It's possible. I would thought to do some simple modelling actually, which would give you some idea of the sort of things that might be seen. You see something different, then the modelling was wrong. And I would have thought, yes, that was a prospect there. You know, enormous amount of.
I think you have done something not more than 10 years ago in that direction, but since then, with this mode combination.
I got more worried about whether dynamo works, but something like what Dimitri was talking about for the solar case.
So
that's the kind of thing which would not make too many assumptions and then.
If you invite me to formulate my opinion, my point is that we have to make a clear distinction between two levels of models, simple, oversimplified models which are directed to comparison with observations. Here we anticipate for the time being that such things as turbulent diffusivity, alpha effect, and things like that do exist. And the other level is clarification why it works. Maybe the concept of alpha effect and turbulent diffusivity is not very deep. We have to replace it by something else, and so on. We are dealing with transport processes with magnetic field. There people are doing the same in, say, TV technique and electrotechnique and so on, and they separate strongly two levels of problems. How to understand why copper is conductor and not insulator, one level of problem. Second level of problem, not to ask such things, and how to extract conductivity of copper from the tables and how to apply it for practical reasons. And they invested much more efforts, money, and ideas as we can expect to invest in all visible future, and didn't overcome this bifurcation between two levels of theory. And it would be, if we concentrate in such framework of in such statement of problem, of course, questions which Rainer is asking are answerable, and maybe not on such high level of, not say on such high pro level, but why not?
So thank you for your positive statement. So there's some questions might be answerable within the next, I don't know, years. So I think we have 6 o'clock now. We should stop, and thank everybody for contributing to the discussion, and we can continue tomorrow with another series of unsolved problems. Okay, thank you.